off we go. So I'm going to teach something called bitwise operators today. That's all we have time for. So what is that, you might ask? It is, well, operators, some sort of math kind of thing that works on the bits of an individual number. So we have to go back to how things are arranged in binary, because bits are the ones and zeros, right? Like this is a binary number, this is a byte. 1, 2, 3, 4, 5, 6, 7. Now it's a byte. And each individual digit, each individual binary digit, that's what we call a bit, right? It's short for binary digit. So I'm going to teach you how to go inside of like an int and pick out, like, is that third bit a 1 or is it a 0? All right, and we'll find that that is useful. So let's first remember what binary is all about. So, because bitwise operators, what they're going to do is they're going to work on the bits. They're going to give us that access. So a bit is a binary digit, and it's a 0 or a 1. Let's remember what binary is all about. So let's say I give you this number in binary, 1011 base 2. Do you remember how to expand this and get back to decimal? It's going to be what? This is 1 times 2 to the 0, right? 1 times 2 to the 0 plus 1 times 2 to the 1 plus 0 times 2 squared plus a 1 times 2 cubed time, which is going to be equal to 2 or 8 plus 0 plus 2 plus 1, right? Which is 11. 11 base 10, that's what it really was representing. Remember that? So if we did a slightly longer number, 10011, that's going to be 1 times 2 to the 0 plus 1 times 2 to the 1 plus nothing for the 2 squared and 2 cubes place, but 1 times 2 to the 4. That's 16 plus 2 plus 1. That makes 19 for that one. All right. And then 0 in binary land, you remember that integers take a bunch of binary digits, more than just one. The number 0 is just a bunch of zeros. It's just like as long as you can have zeros, that's 0. So you know that ints maybe are 32 bits long, 4 bytes long. Remember reading about that? So that means the number 0 encoded as an integer, as the int type, is deep down in memory. It's 32 0 bits. All right, 32 zeros in the int 0. Because every int needs to be 32 bits long. Yeah, say which values each of those 32 bits hold. Okay. I've also only been talking about positive numbers in binary. I haven't shown you how to represent negative numbers in binary. It's like there's no negative sign inside of a computer. How do you represent that in terms of just zeros and ones? We'll get to that. Because int totally holds negative numbers too. We're going to figure out like how does it do it. But remember that there's going to be 32 bits in every int. So 0 is that. The number 1 would be a bunch of zeros and then a 1 at the end. Just 0 padded. Are there any questions about any of that before I go into more detail? Like this is kind of a review, hopefully. Because I want to talk about negative numbers, because that's been swept under the rug, hasn't it? Like what in the world should negative 1 be as a 32-bit integer? I got to choose some ones and zeros carefully and somehow get negative 1 out of the deal. How do I do that? So the trick is noticing that, well, whatever negative 1 should be, as far as 32-bit numbers are concerned, negative 1, the whole point of being a negative number is like I could add it to positive 1. Whatever negative 1 is, it's the number that when I add it to positive 1, I get 0, right? And that's what we can use to discover what in the world negative 1 should be in binary. I do not want to write 32 digits, so let's pretend all our numbers are only 4 bits right now. Okay, let's pretend we're only working with 4-bit numbers. And all right, I'm going to come up with some fancy number such that when I add it to the number 1 in 4-bit land, let's pretend, instead of 32-bit land, some question mark bits here, I got to add to 1 and get 0, all right? Because whatever the answer is up here becomes negative 1. Does that make sense? That's where we have to discover this now. So, okay, we're going to do addition in binary. We got to start with this digit. What should this be? It could either be a 0 or a 1. Well, if it's a 0, do you see how that is now wrong? 0 plus 1 is 1. That would force a 1 down here. So I can't put a 0 as the rightmost bit of negative 1, can I? This must be a 1. Does that make sense to us? So I'm going to keep playing that game. So 1 plus 1 in binary is 2, which is 1, 0, right? So I got to carry a 1. 1, 0. And now, again, I'm playing this game with this next binary digit, this next bit. What should negative 1 be for the second bit? Or bit number 1 or whatever. Well, again, if I make it a 0, do you see how that carried 1 is ruining the day? If I make it a 0, it's going to force a 1 down there. I don't want a 1 down there. So I must next put another 1. See that? There must be the next bit must also be 1. All right, and that'll force a 0 here. But also carry this one, and for the same reason, I can't put a 0 here because that would force a 1 down here, so -1 must be that for that bit. Carry the 1. Again, you need to put a 1 here. And then we're going to pretend we have 4-bit numbers. Like the answer, 1 plus 1 is 1, 0. You put the 0 down in that place, then you carry a 1 out. But we're pretending we only have 4-bit numbers, so there's no room for that last carried out 1. Okay, and it just kind of vanishes. And that is the magic of negative numbers. So that means all 1s is -1. Does that make sense? That's it. We found it. And so in 32-bit land, it would be 32 1s. That is -1 as an int. Okay? So -1 in binary is all 1s, and the nice thing about that is that, like, the whole reason it works is that last carry out from the last bit doesn't really do anything because we don't have enough room for it. It just kind of vanishes, which is perfect. Okay, so that means 1, 1, 1, 1 is equivalent to -1. But it's also equivalent to 15, isn't it? We've done that expansion before, haven't we? Is it 15 or is it -1? It depends. Now it depends, okay? Depends on if we're encoding negative numbers or not. If we have chosen to use negative numbers in our type, like ints have, you're giving up some large numbers to have negative numbers, okay? That's the trade-off we have to make. Is this 15 or is it -1? It depends on your interpretation, all right? So let's do -2. What should -2 be? Well, it's whatever, when you add it with binary 2, positive 2, you get 0. So let's figure out what -2 should be. All right, well, finally, this could not be a 1 like it was for -1. I'm forced to put a 0 here to make the 0 at the bottom, and then I'm going to play the -1 game. Like, okay, I can't make this a 0 because then I put a 1 there, so this must be a 1, it's got to carry, which means this must be a 1, it's got to carry, this must be a 1, it's got to carry, and it carries out and vanishes. So apparently, 1, 1, 1's, all 1s except for the last bit makes -2. 1, 1, 1, 0. That's equivalent to -2. If it were 32 bits long, it would be 31 1s, then a 0 to make -2.
If you had a negative really large number, would it create an overflow?
It just wouldn't be representable. It's just the idea is we have given up the ability of holding those large numbers. Like, we're going to interpret that as a negative number from now on. Yeah, but we will get to overflow. That's another important thing. Yeah, so does this process kind of make sense? We can discover what the negative version of any number should be for a given bit size. That's the secret. Yeah.
How is adding like the 1 and 1?
This right here?
Yeah.
Well, in binary, remember that 1 plus 1, it's really 2. But in binary, it's 1, 0. You have to carry. Binary 2 is 1, 0. Yeah. That's the secret there. There's a faster way, though. There's a trick. It's called 2's complement form is the way that we've chosen to like store our negative numbers inside of a computer. And so the secret is, if you want to go from positive to negative very quickly, you can do this 2's complement translation. Here's the trick. If you want to negate a number, either negative to positive or positive to negative, you flip all the bits, so 1s become 0s, 0s become 1s, and then you add 1 to whatever that result is. So like, all right, I want to go from positive 1 to -1. Well, I'll just flip all the bits. That becomes 1, 1, 1, 0, and then I'll add 1 to that. Whee! So 1, 1, 1, 1. Very quick. And it works in the reverse order as well. So like, I want to go from -1 in 4-bit land to positive 1. How do I negate this number? Well, I'll flip all the bits, 0, 0, 0, 0, and then I'll add 1, 0, 0, 0, 1. Okay? So that's a quicker way to discover the negative version of any number and to go back and forth. So that's what's really happening inside the computer. But we know how to discover it now. We know how it was discovered, essentially. So we're giving up some large positive numbers to store negative numbers. Right? That's the difference between int and unsigned int, if you read about that in your book. Okay? Are we ready to talk about code now and talk about operators that can access individual bits? Does all make enough sense for now? All right. So I'd like to talk about the first bitwise operator. It's called the bitwise AND operator. All right. So let me motivate the reason, like, why would you care about, I want to know if this bit right here is a 0 or a 1, right? It helps you with space saving. So sometimes it's really nice to store things other than numbers inside of numbers, to use numbers as something other than a number. For example, you can store, well, if you got 32 bits for an int, you can store 32 separate bools inside of an int, can't you? If you had a way to pick out each piece. Like, you have one big long int that's 32 bits long. You could use each bit, if you had a way to access each bit, and I'm showing you how, you could use each bit for something, and that would pack it tightly together and save you a lot of space, rather than Boolean variables, which I think every bool variable is a byte long, so you're wasting a lot of bits there. So like you could say that, okay, this bit here, if you go and check it, if it's a 1, that means you're like, this is a video game and your character has an extra life or something. So like you're saving on memory if you do it this way. You have an extra life, and then like maybe if this bit is set, it means your character is riding a horse or something, like in Zelda. Something like that. Like you could use that. You could use an int to represent 32 different bools, among other things. Okay, so that's the motivation, and that saves a lot of space. And so yeah, I'm going to show you how to do things to individual bits of a number. Like, tell me if this is a 1 or a 0. Set it to a 1 or a 0. If like the character gets on the horse finally, flip this. I'll show you how. Okay, so let's talk about it. The bitwise AND operation does the Boolean AND. We know what the truth table for AND is, right? We remember that. It's going to do the Boolean AND on each bit of a number, and you line up. You give it 2 numbers, and it's going to line them up and like do the bitwise. Or going to do the logical AND on each bit. All right. So let me show you what that means. So remember that logical AND was this 2 ampersands. So we're going to get rid of an ampersand, and that will be bitwise AND. Okay. So it uses this ampersand operation. So here's the trick. You give it 2 numbers. It's like you bitwise AND 2 numbers together. So here are 2 4-bit numbers, let's pretend, instead of 32 bits. So let's say I've got these 2 binary numbers, and I want to bitwise AND them. Here's what's going to happen. The bitwise AND operation takes the 2 numbers, and it lines their bits up, and it will produce a 3rd number. All right? It has nothing to do with math. It's going to produce a number in a weird way, and this is how. All right? It's going to say that 1 means true and 0 means false. We know that. And it's going to do the logical AND on each of those bits. It's going to line them up. All right? So it lines up these guys, 1 and 0. So it's true and false, and we're ANDing them. Remember what true ANDed with false is? So it's essentially going to do this. True ANDed with false, because that's what it's going to interpret these as. And what is true ANDed with false? False. Good. Now it'll give back false, and so it will produce the bit 0 down here. It will produce a 3rd number based on the other 2. All right? And then it'll line these guys up and be like, oh, true ANDed with true is true. Any false anywhere, false. True ANDed with false again, still false. So it will produce this number. All right, so what were these numbers? It has nothing to do with math. It's bitwise stuff. So this was what? This was 8, 9, 10, 11. That was 11 base 10. And we bitwise ANDed it with the number 6 base 10. And somehow we ended up with the number 2 base 10. Okay, so it has nothing to do with addition, subtraction. It's not mathematical. It's bitwise. Okay? Are there any questions about that? So you give it 2 numbers, it's going to line up the bits and do logical AND on each of them. All right? And it's the single ampersand that gives you that. And I'm so sorry, right? Because this is like the 3rd thing that a single ampersand does, depending on how you use it in code. So like we know that ampersand is for address of, outside of a type otherwise. It's like next to a variable name. We know that it means reference if it's part of a type. Well, now it also means bitwise AND. I'm so sorry. You'll know from context clues which one, though. So, what's that? There's just so many characters on a keyboard, I guess. I had to pick one. I think this was probably the original one, though. This came in the C language, bitwise AND. References. I guess address of also came from the C language. So those 2 were the originals, and then reference was new from C++. So the C++ people made it worse. But yeah, I don't know the original reasons. All right, does that make enough sense for now? Like, you might be wondering what is this good for? Let me tell you what it's good for. The idea of bitwise AND is that it's meant for extracting bits. Tell me if this bit is a 1 or a 0 right now. All right, here's the trick. Let's say I've got some number, like this big thing, and let's pretend it's only 4 bits long. And I would like to figure out, like, is this bit right here set? All right, is this bit right here set? First of all, there's a numbering to bits. It goes from the rightmost one. It's like, starts at 0, of course, because this is computer science. So this is bit 0. This rightmost one, that's bit 0. This is bit number 1. This is bit number 2. This is bit number 3. So essentially, I want to ask the question, is bit number 3 set right now? What you can do is you can bitwise AND with the number where there's a 1 in the position you want to check and a 0 everywhere else. Do you see how this is the number where only the third bit is set? Third bit set only. Do you see how these zeros, falses, will force zeros everywhere other than the place you care about checking, right? 0, 0, 0. And then this 1 will pick out that one bit that you really wanted to know about, right? And it will be a 1 result if it was set. See that? If this bit was not set, do you see how you get the number 0 as your output? That's what you could check against to know if that particular bit was set. Do you see that? So if it was a 1, it will make some number other than 0. But if it was a 0 after all, it will make the final number 0. You can check against that in an if statement to see if that particular bit was set, right? So that's us doing what? 11 base 10 ANDed with the number 8. 8 base 10. Sorry, it's so small. And that will produce the number 8 base 10. So just something other than 0 meant that it was set. Okay, so that's the trick. And I think I want to show you this in code now. Does that make enough sense? Please yell at me if it does not. But we're doing stuff with the individual bits of a number. Okay, so what did we do? We did 11 ANDed with 6. So 11 ANDed with 6. And we did 11 ANDed with 8 as well. Okay. So the results were 2 and 8, like we saw here. It's doing it. It's giving us those numbers back, but it's really not doing any math. So the whole point of doing this one was we wanted to check if that third bit was set. So because the answer, or the result, wasn't 0, that means bit 3 was set. And that's what you could do in like an if statement. Okay? So that's bitwise AND. It's good for extracting bits, seeing if they were set. All right? Are we ready for the next one? Yeah. Set means a 1, unset means a 0. That's what I mean by that, yeah. Any other question? All right, so let's go to OR. There's bitwise OR, just like there's logical OR, right? So just like we got rid of a character, this was logical OR, 2 piped characters. You're going to get rid of one of those, and bitwise OR becomes just that single pipe character, right? So what it's going to do, as you would expect, is going to OR together every bit after it lines them up, all right? And so let's say I've got this number 1 0 0 1 1 1 0 0. I can bitwise OR them together. Okay, it's not a 1, it's an OR symbol. And then it's going to line them up and do the OR. All right. So like it's going to take these guys and be like, all right, that's a true ORed with a false. And the answer is true, right? So it'll put a 1 down there. The only time it's false is if both are false, so that's a 0. But as long as somebody's a 1, then the result gets a 1 down there. All right, so what did we just do? We did, this was 9, right? 9 ORed with 12, and somehow that produced 13. So it's not mathematical, it's bitwise, okay? So that's what it does. And bitwise OR is good for setting a bit, to make sure it's a 1 right now, all right? Just make sure that there's a 1 in that location if there isn't one already, all right? So let's say we've got a number, 1 0 1 0. Remember the bit ordering. This is bit 0, this is bit 1, this is bit 2, this is bit 3. Let's say we like to take this number and make sure that bit 0 is set, okay? Do you see what you would OR by to do it? You want to preserve everything else. You're going to put a 0 everywhere else. You see how that's going to preserve everything? Keep it all there if it was a 1. Stay 0 if it was a 0. And then you're going to put a 1 in the bit position that you want to make sure is set. Okay? That'll be the number where the 0th bit only is set, which is just the number 1. Okay? And so that will produce, well, it will preserve everything else, right? The 1 OR with 0 is 1, 0 over 0 is still 0. It's going to take everything else, going to bring these guys down, 1 0 1, and then it's going to make sure that this bit is set to a 1. Okay? So that was doing what? This is the number 10 ORed with 1, produces 11. So this time it actually ended up doing addition, but you can't bank on that. All right. If it was already 11, it would keep it 11. Just make sure it's set. That's what OR is good for. Okay. Any questions about that one? Yes?
You said and is for checking and then or is for making?
Yep. And is for checking. Like, it'll give you back a 0 number or a non-zero number when you do the and, based on whether or not that was set. And then or is to make sure it's set. Put a 1 there for sure. Even if there's one already there, keep it there. Yeah. So let me show that to you in code. I guess I'll need to separate. Well, let's do these guys. Be like, see out. What do we do? 9 ORed with 12. And then it was 10 ORed with 1. Cool. And so we see our 13 and our 11. Okay. So you don't really want to interpret these as numbers usually. That doesn't really matter. But yeah, what this operation did, this made sure, right? Make sure that the 0th bit is set. Okay, that's what bitwise OR is good for. I think that's what I wanted to say. Questions about that one? We good? All right. You know that there's a negation, right? So what's the bitwise version of that? It's called bitwise not, or complement. All right. So that we know that there was a logical negation with the exclamation point. We can't get rid of any symbols with that one, though, sadly. So we're just going to throw that one away and use a different character. All right. So bitwise not, what it's going to do is it's going to flip all the bits of a number that negates them all. Right. True becomes false. False becomes true. And then the one that we've chosen to mean bitwise not is going to be the tilde character. Okay. So that's the one that's finally a little bit different. All right. And bitwise not only takes one number. It's going to just negate every bit of a single number. Like you give it tilde this number in binary, it will produce this number, 0, 1, 1, 0. All the trues became falses, all the falses became trues. It negated them all. Okay? So what is this? This is the number 9. Flip all the bits in 4-bit land, it became 6 somehow. Okay? So let me show that to you, and let's see. Before I do, though, I also need to make a makefile. Before I do any of that, remember that this depends on how big. Bitwise not is going to really depend on how wide your type is. So ints, for example, if you did 9, if you started with 9 and you wanted to flip all the bits of 9 as an int, remember that it's not just 1001, it's a ridiculous amount of zeros, right? And then 1001. And so when, as an int, you're flipping all the bits, you're doing the bitwise negation, you're going to end up with a giant number, aren't you? Does that make sense? But this is actually one of the numbers that we've chosen to mean negative numbers as an int. So it's so big it becomes negative, okay? That's the problem. That's what's going to happen. As an unsigned integer, if you did this as an unsigned int, it would make a giant number, legitimately. Okay, but remember that there's extra zeros to pad it up to 32 bits wide for an int. Yeah, so this will give us a way to do negation without doing negation. So let me show you the 9 first of all. And then I'll make a makefile. I got to do all these things in a good order. All right, so here is tilde 9. Right. So remember, it's going to make a big long number with a bunch of ones, 1, 1, 1, 1, 1, all the way to 0, 1, 1, 0. That's what it's going to produce. And what number is that? We might ask. As far as C++ is concerned, it's negative 10. And that should make sense, right? Because what is the way that we make a negative number? What's 2's complement? You flip all the bits, and then you add 1. So it's 1 away from negative 9. You see that? That's the trick. That's what's happening there. So let's make a function that like does the negation in that 2-part process in a bitwise way that we kind of understand. All right. So let's do that after we make a makefile. So I want to make a makefile just to remember, even though this is a single file, we can just compile it all at once. It's not a big deal. But let's remember about makefiles. So I just want a rule that just keeps doing this one, C++. All right. So I'll make a new file called makefile. Got to be with a capital M. And I'll make a rule for the thing that I care about. Bitwise is the name of my target. What needs to exist in order for me to make this thing? I could go through the .o stuff, but I'll just start because it's just one file. I'll just do the one file. I just have to compile it anyway. So there's that one, and it requires bitwise.cpp to exist, and then to create the bitwise executable from bitwise.cpp. We're going to say g++ bitwise.cpp-o bitwise. Okay? And so instead of doing it that way, we can now say make bitwise, or just make, because that's the first and only rule. And it's just going to notice like it's up to date. We don't need to do anything yet, which is nice. It's efficient. All right, so let's now do a negate 2's complement function. It'll take a number and it will negate it in the 2's complement way by flipping all the bits and adding 1 this way. Flip all the bits and add 1. My green examples here. All right, because it's very close. This is very close to negating 9, isn't it? So let's make a function and call it negate 2's complement on 9. So it's going to be a function that takes an int and gives back an int. And so what's its job? It will return negative n without actually saying negative n or multiplying them by 1, using 2's complement, using the way that we know it's encoded inside of memory. So, all right, how do you take your number n and negate it using 2's complement? Well, you're going to flip all the bits and add 1. So I'll flip all the bits of n, and then I'll add 1 to that. And that will produce the negative version of that number. All right, and so I'm calling it down here on 9. And so it's going to jump up here and produce, I could say make now, /bitwise. There's my negative 9. It's going to return the correct thing. All right, so that's secretly what the CPU is doing when you tell it to negate something for you. All right, it can do it a bit faster because it knows that people usually want to do that, but you can split it up. That's the secret way that that it's really doing it under the hood. Okay. Any questions about that? It's fun stuff. Yeah. What do you mean? Why this one didn't produce negative 10? Because I did the tilde up here, and you know that tilde 9, you understand that that creates negative 10, right? And then I added 1. Negative 10 plus 1 is negative 9. That's what we needed. Yeah. Other questions? All right. Well, I don't know the best way to do this. I'm going to... I guess I can show you... I don't know what to give you, honestly, but I have a question for you, okay? I'd like you to go to the written-ice page, please, and I'll stop attendance if I can remember after we do this. But as a group, I have something for you to ponder, all right? You can elect a leader to write your answer in here, but I would like you to discuss the following. I'd like you to write some code that does not set, but unsets the 5th bit of a number called x. So somebody's made a number called x, set it to something, and your job is to unset the 5th bit of x with some code. All right? You can do it in one line if you want to be fancy, but let's say here's my x. Here's what I want you to do. So like here's 1, 1, 1. Let me move this down where it's 1, 1, 1. 0, 1, 0, 1, 1. So which is bit 5? This is bit 0, 1, 2, 3, 4, 5. There's that one. So that's the bit I care about. I want to unset it. So I want to produce, I want to change x into the number where everything else is preserved. 0, 1, 0, 1, 1. But make sure this thing is a 0. Does the setup make sense? That's what I'd like you to try. All right. And so that 1 became a 0. How can you do that? All right. The trick is like set bit 5 to a 0, even if it's already a 0. Keep it a 0. All right, write some code that would do that. And my hint to you is you can do it with a not and an and. So that is the tilde and the ampersand. It's going to do logical and on each bit. All right, and then you can read my second hint yourself. Okay, so give that a try. You can do it in one line if you want, but that's the secret. Here is, you know that not flips all the bits, right? Let me give you at least a picture of and. And is going to be logical and on each bit. So not flips all the bits and does that. All right? Any questions about the question? See if you can figure it out. All right? I've given you a way to set. I've given you a way to check. I haven't told you how to unset. But there's a combination. All right? There's a way to do it. See if you can get it. Was that enough time, everybody? Kind of either you see it or you don't see it, kind of a question. Let's see if we saw it, some of us. Nope. I have spilt water on my tablet, though. Let me fix that. There we go. Any takers? 2 takers. Nice. It's okay if you don't see it. It's a little bit of a harder question, but nice. Group 27. Whoever you are. Proud of you. That's going to be it. And I will try to break it down for you. So, let's see here. Very nice. Very nice. What? Let's say, here's my number again. I want to produce a number, right? I would like to do the following. This is kind of the goal. It was 1, 1, 1, 0, 1, 0, 1, 1. If that was the number, that means there were also some zeros way over here, right? We'll deal with that later. But this is bit number 0, 1, 2, 3, 4, 5. That's the one I care about unsetting. And what I want to do is something magical, right, that eventually produces this number, right? 1, 1, 0, 0, 1, 0, 1, 1. So everything's the same except for that one. You can't use OR, right? Because OR would just like preserve. OR would totally preserve. You put an OR there with a 0, even a 0. Definitely a 1 would keep it a 1. So you cannot use OR for this. Does that make sense? OR is out the window. So the only other option is kind of AND, right? And what we're going to do is we're going to AND with, you see which number you could AND with? Well, if I want to preserve everything, I better put a 1 in all the bits that I want to preserve. I don't know if they're 1s or 0s. I haven't looked at them really. So I also want 1s way out here too, huh? Right? Whatever those numbers were, preserve them, except for the bit I don't like. I would like to put a 0 there. Do you see how that will force a 0 in that one position, keeping everything else? Does that make sense to us? That will be the trick. And then now the question is, how do I come up with this weird number with a bunch of 1s, 1, 0, bit 5, and then a bunch of 1s, right? The easier way of thinking about that number is, whatever it is, it could be this, right? I could get it by doing this. I could start with a number with just this one set. You see that? Just a bunch of zeros, and then just a 1 right there. 1, 2, 3, right? So bit 0, 1, 2, 3, 4, 5. Do you see how if I negated that number, this number right here, that would put a 0 at bit 5 and a 1 everywhere else. You see it? That's the trick. That's the trick right there. And so what is this number with bit 5 set? This is 1, 2, 4, 8, 16, 32. Okay? The number 32, so tilde 32 will produce that number. And now if I AND by that, that's like what you would fill in. If you wanted to do it in one line, it would be x equals blank. And now the blank is going to be, well, take x, bitwise AND it, with a number with a 0 right there and a 1 everywhere else, which is tilde 32. All right, I'll draw that in a different color. That's your answer. X ANDed with tilde 32. That would unset that bit. Cool. Force it to be a 0. Are there any questions about that? Do you see why it works? It's pretty neat, I think. All right, let's do a couple more bitwise operators. There's a few of them. There's more even than these. I would like to teach you about bitwise exclusive OR, XOR for short. All right, stands for exclusive OR, just like that. So the OR that we've been using day to day is called inclusive OR. All right, that's our regular OR. This is called exclusive OR. And what it's going to do is something very similar to normal OR. Here's regular OR, right? We know. Let me compare it to regular OR. What our regular OR does, I'll draw the truth table. So regular OR does the following. You give it two things, x and y, and it'll do x ORed with y. Let me draw that truth table for us. This will be true, 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 false, false, true, false, false. Boop. And that will produce true, 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 false, right? That's our normal OR. That's the one we know. Inclusive OR is what that's really called. It's technically known as inclusive OR. It gives back true when one or at least one side is true. Okay, that's what it does. Exclusive OR likes to be exclusive. It likes to make sure that only one side was true. All right, exclusive OR. Here's its truth table. X, Y, X, exclusive ORed with Y. X ORed with Y. What do we say? What are my options? True, 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 false, false, true, false, false. So it's the same for all these guys. This is false. Okay, one's true, one's true. This is where it differs. It wants to exclusively be one side true. So it's going to say false for that one. That's the one difference. Okay, that's what exclusive OR is all about. And yeah, it's true only if one of the sides are true. It's only true if they're different, essentially. So the logical exclusive OR operator is your not equals to on bools. Okay, but in bitwise land, the bitwise exclusive OR is called the caret. That's the caret operator. That's what they chose it to be. And that's why you ran into trouble maybe at the start of the semester thinking that that meant power, right? It's really doing something really weird with bits of a number. It's not doing a power computation, okay? So that's why. That's the secret. So here is bitwise exclusive OR. Let's do like 1011 exclusive OR with 0101. What will this do? It'll line them up. Well, it didn't line them up very well myself, did I? It'll line them up and then start doing exclusive OR. So true exclusive OR with true, because it's exclusive OR, that's false now. That produces a 0. It's a 1 only when they're different. That's how I like to remember it. Okay, so that produces that number. All right, which was, what was this? This was 11 exclusive ORed with 5 produced 15 minus 1, so 14. Somehow 14, okay? So that's that one. That's exclusive OR. Okay, but that one is different. It is useful for some things, I promise. Let me at least show it to you in code so that we have that for posterity. What did we have here? It was 11 exclusive ORed with 5. 14. Cool. All right. One good thing that it's for is secretly deep down inside of your computer. You'll have to wait until CSCI 45 to fully understand this. Addition, all the addition circuitry inside of every CPU is doing a bunch of exclusive ORs, surprisingly. Exclusive OR, if you squint, it's just like addition on a single bit, isn't it? Because, watch, 0 exclusive OR with 0, that's 0, right? So false. That's the same as 0 plus 0, isn't it? 0 exclusive OR with 1, that's a 1, right? Because they're different. That's the same as 0 plus 1. Ooh. Same for 1 and 0. 1 exclusive OR with 0 is 1, same as 1 plus 0. And then 1 exclusive OR with 1 is 0, which is actually true for 1 plus 1 in bitwise land, isn't it? Because the answer is got to carry the 1. The answer in that particular position is a 0. So exclusive OR is kind of like addition, and secretly inside of your computer, it's doing a bunch of exclusive ORs when it produces addition. That's kind of cool. All right, you'll have to wait a little while longer to fully understand the power of that, but that's one reason to love it. Okay, it's good for other things though. I'm going to show you. Let's see. That's all that I want to show us for now for exclusive OR. It's the caret character. The last one is probably one of the most useful bitwise operators. They're called the shifting operators. Right? These came before the cout and cin. This is like from the C language, not the C++. these operators you know and love, right, from C out and CN, they really were bitwise operators. They've been overloaded by C++ because people don't use them too often. But this is the left shift operator because that's a left arrow, right? And this is the right shift operator. Okay, so yeah, they do kind of what you would expect. You have a number and you can shift it. So let's say we've got, let's do left shift. What you do is you have some number, 1, 0, 1, 1, or whatever, and you say, I want to left shift that by 2 bits. So you give some integer here. And what it'll do is it'll move this number to the left by 2 bits. Okay, so that's what it's going to do. It's going to say, all right, I'm going to start with 1, 0, 1, 1. I'm going to start shoving it to the left, moving it 2 bits to the left, and that brings in new places for new bits, doesn't it? Moving it to the left. That means then it's going to produce a bigger number. Okay, and that's what's going to happen when you do a left shift. And so what number does it produce? What number is this to start, first of all? 8, 9, 10, 11. This is 11, base 10. This is the 1's place, the 2's place, the 4's place, the 8's place, 16's, the 32's place. This will become 44. 11 becomes 44 when shifting right or shifting left by 2. That's kind of interesting. What are we doing? All right. So in general, there's a trick to be seen here, right? Let's start with the number 3. 0, 0, 1, 1. Shift that left by 1 bit. This is the number 3, right? It will produce 0, 0, 1, 1. Shift it left, brings in a new place, right? For a 0, that creates 6, doesn't it? So it's doing some multiplication, isn't it? What's happening is it's taking the original number and it's multiplying it by 2 to the power of however many times you shifted. That's the secret. That's what's going on. In general, left shift is going to multiply by a power of 2. Okay, that's what's going to happen. So you start with some number, you left shift by a certain amount. What will be produced is that original number times 2 to the ith power. So like this, because I left shifted 11 by 2, I multiplied by 2 squared. Multiplied by 4. Okay, produced 44. Does that make sense? That's what left shift will do. It'll move the bits of a number over by a certain number that you specify. Okay, so that's left shift. It's a good way to multiply by powers of 2 and move bits around. Okay, so let me show you that one. Just in code so we have it later. Let's do that. And so I'll do, what was it? It was 11, right? 11 left shifted by 2 is going to multiply it by 4. Cool, there's my 44. Beautiful. Multiplying by a power of 2. Right shift, as you would expect, is going to shift bits to the right. And actually, it's going to have to chop some off, usually, won't it? So, all right. Right shift is going to shift bits to the right. And here's kind of how I want you to think about it. I won't explain it further until I show you a drawing. So let's start with this number. This is the number 5, right? 4 plus 1 is 5. So I can right shift that by 1, and it will produce the following. What it's going to do is it's going to right shift it, right? And so that is going to like move all the bits to the right and bring in a new one over here. Does that make sense? So that means we've run out of room for this one, and we're going to get rid of it. Okay, so it produces on the right side 0, 0, 1, 0 now. At the expense of that one, it brought in a new one on the left, a new bit position on the left, which it will fill, in this case, with a 0. Okay? And so what it just did, it just like shifting left is going to multiply by a power of 2. It's going to divide integer division land by a power of 2. So this produces the number 2, doesn't it? Okay? So that's 5 divided by 2 to the first power. That produces the number 2. Integer division is what it's doing then. Okay? So it's doing division by a power of 2. But there is actually something fancier that's going on. If you're doing right shift on normal integers, things that can be negative, it might bring in a 1 sometimes. Like this bit doesn't have to always be a 0. It's going to bring in a 1. It's going to make it so that it can do the right kind of division. It'll bring in a 1 if it was negative. All right. The secret is that if there is a 1 in the last bit of a number, the 31st bit of a number, that's the one that we're marking as negative. We've given up that large bit value for whatever value it used to mean, right? We've chosen to mean that's a negative marker for us now. So that means it's a negative number. And if you right shift a negative number, you want to keep it negative, right? So you want to keep the 1 up there. That's the secret, right? That's why it's going to bring in a 1 if if you right shift on a normal int. If you right shift on an unsigned int, which is always positive, or negative, never negative, sorry, it can be 0, then it's just always going to divide as well. Okay, so it has to be a little careful with negative numbers. That's all I'm trying to say. You don't have to worry too much about that, but that is the shifting in the opposite direction. All right, for a positive number, it'll just bring in a 0. All right, so let's do that one. 5 right shifted by 1, we'll divide it by 2. Divide by 2 to the power of 1, right? So there it is. Produces just 2. All right. Does that make no sense? Yes? What do you mean? They're different operators. This is the left shift. I have to type left shift if I want left shift. Oh, I see. It's because there's 2 ints on both sides. If there was a cout on one side, C++ would know, like, oh, okay, you want to print something. Yeah. It's due to the types. It knows. Because really, this is the operator greater than, and somebody implemented it for the cout type and also for int types. Yeah. Good question. Let's see here. Any other questions? Because by itself, shifts are cool. I mean, sure, that's nice to do division and multiplication in a different way. Actually, before I move on, I should say that back in the day, with the first computers, first processors, it took a long time, relatively, inside of a CPU to do multiplication. And so if you were ever multiplying or dividing by a power of 2, it would turn your, like if you actually try to do this instead, you were like, cout 11 times 4. It would actually turn it into this code with a left shift, because that's faster inside the CPU to do that rather than multiplication. These days it's pretty much the same amount of time, but it used to take much, much longer to do a multiplication, and especially in a division. So the compiler likes to change around your code into the most efficient way, and sometimes that involves doing bitwise stuff. So that's kind of cool to think about. So in addition to that, and just understanding that, bitwise shifts are good in combination with the other things to actually get what you want. So let's say, like, we go back to this example, like I needed to make the number 32 and come up with that magic number. I didn't really. So here's how. Here's how you can get that very quickly without having to calculate, like do powers of 2 on your hand like I do. If you want to, for example, if you want to set the third bit of a number n, right? Want to set the third bit of some number, you are going to OR by a number, right? I want to set the third bit of a number. Here's a number. Here's bit 0, 1, 2, 3. I want to set the third bit of a number, right? So I want to OR with this number, right? How do I get this number very quickly? Well, I could just start with 1 and left shift it by 3. Do you see that? Just immediately I have the number I need. I don't have to go calculating, okay, that's 1, 2, 4, that's the number 8. I don't have to worry. Just like let the shift handle it. See how nice that is? That's the trick for that, all right? That will do what I want and produce the answer that I care about. Okay. Same with extracting bits. All right, if I want to extract the third bit of a number n, then I want to AND it. I want to bitwise AND it by the number with the third bit set only, and that's 1 left shifted by 3. I will produce 8 that way. Question? Yes, but how would you, like if it was a large number? Yeah, that would take a long time to type and also to think of what it should be. I just want to know, okay, it's the third bit, it's the 12th bit, whatever number, whatever power 2 that is. Very quick, okay? Yeah, but you could just type 8 like I was doing for the small ones, but for the big ones, this is totally worth it. So like I want to extract the third bit of a number, 0, 0, 1, 1. I want to AND by this, whatever that is. We know it's 8, but like very quickly you can get at that with 1 left shifted by 3. Let C++ do the work for you, and that will produce the number 0, which tells you that, oh, it wasn't set. That bit was not set. Okay? So yeah, that's what 1 left shifted by 3 does. Like it starts with 1, right? And it shifts it to the left, so it brings in 3 new bits, which it places zeros in, and there's your number with the third bit set. Beautiful. That's so nice. And so let's do both of those. Be like, all right, I've got what was I doing before? I was doing these guys, right? I was doing like 11 ANDed with 8. That's kind of silly, right? I just want to set the third, or check if the third bit was set. So I'm going to really do what I should have done is cout, let's see, 11 ANDed with 1 left shifted by 3. That will produce that 8 that I had up there. So instead of like hard coding it and trying to like you pull out a calculator, I can just do this. It's much easier, right? Same with this one. See, I kind of transformed this one into that one. So I took, oops. Oh man, let's do it this way. Let's just start from that one actually. So like I want to change this one, make it better, and I want to change also the one with the or, make it better. All right, so that does not require thought. In a way that does not require thought. All right, that's the same as 1 left shifted by 3. All right, and this one is like I want to make sure that the 0th bit is set. So I mean we know that that is 1, but if you want to make a function to do this, this is the same as 1 left shifted by 0. Right? It's like that's the bit I care about, the 0th bit. Like that's easy for a programmer to look at and understand. Oh, great, I care about the 0th bit. I'm doing something with it right now. Right? And so you get the same answer, of course, but less thought on your end, which is always better. Less opportunity for errors. Right, yeah, I think that's what I wanted to say about that. Are there any questions about those ideas? So shifting plus these other things are very helpful. All right. So I have one last question for you for the day. I would like you to try to write some code this time. Go back to that written nice page. I'll give you a few minutes. We got time. You can edit your original ones if you'd like. I'd like you to write some code that toggles, does not set, does not unset, it toggles it, turns it on and off like a little switch. Toggles the 4th bit of an integer called x. Right? So somebody's giving you an int x. I would like you to toggle the 4th bit of that number x. So if this was the number, it's 1, 0, 1, 0, 1, 0. This is bit number 0, 1, 2, 3, 4, that one right there. Do something to produce 1, 1, 1, 0, 1, 0. All right? Something to get you that. And then if your number was this one, your same code should be able to do the following. If it was this one instead, 1, 1, 1, 0, 1, 0, so it should go back to the start. It should take this one and make it, toggle it to a 0. Does that make sense? Try that. Can you do it? That's the goal. Make that a 0. There's a way to do it on one line, but there's totally a way to do it in multiple lines with like an if statement, right? I think you can do it. Like check if it's set. If it was not set, set it. If it was set, unset it. You know how to do both of those things now from previous examples. Give that a try. So whatever you should do, it should work the same. I'll draw just another example. This is 1, 0, 1, 0, 1, 0. That's bit, sorry, that's not bit 1. That's bit 0, 1, 2, 3, 4. That's the one I care about. Some code that changes that to a 1, 1, 1, 1, 0, 1, 0. And the same code, right, it's toggling it, should also work. If you run that same code on this new number, it should bring it right back to 1, 0, 1, 0, 1, 0. See that? See if you can figure that out. You can do it in one line, but you can totally do it with what you know as well. Try it. What would the long way be? It would be like, all right, if bit 4 is not set, set it. Else, unset it. You could do that. You know how to check if something's set and to set it or unset it. But there is a trick. See if you can find it. Another minute or so. I'll show you my answer. All right, let's see. Let's see what we came up with. Oh, look at this. Nice. We got a good start, a lot of us. Let's see here. Dun, dun, dun. Yeah, let me show you my way. I did notice that not a lot of people submitted though, so I just want to make sure like we're just all shy, right? We're all shy and we're not thoroughly confused, are we? You got to tell me one way or the other. I can't tell the difference. All right, just make sure. Make sure to yell at me if you have any questions. Yes. Okay, cool. Yeah, that's fine. So let's talk about the hard way, the longer way first, because all right, we've got bit 4 of a number that we care about checking, right? We can go back to and. We can go back to and to check that, can't we? I can and with a number with the 4th bit set. And that will tell me, it'll give me 0 if it isn't set, and give me some bigger number if it is set. Do you see how you could make that an if statement? Does that make sense to us? If anding with that special number with the 4th bit set is 0, that means it wasn't set. Else it was. Something like that. That kind of make enough sense? That would be your if statement. And then in the bodies, it's either, all right, I need to set the thing or unset the thing. So we know how to set something with the or, right? We know how to set something with the or, that's this one. Just put or with that special number with the 4th bit set. And you can use the shifts to do that. That would work, okay? You see how you would set the number. If you just found that it was unset, do you see how you would set it? With an or. With like 1 and then 4 zeros at the end of that. What is that, 32 or something? So that would give you that one. And then, otherwise, you'd have to unset it, which would be this all over again. In the else cases body. You see how those would all come together somehow? You were staring at the slides enough. Could you get it? All right, you're going to have to study some more then.
Specifically the numbers that you use as examples. I noticed each of the numbers like 32, 16 are like the values in that position.
Yes.
The 1 or the 3 on the right side usually is whenever you're doing like the and and the or operations.
Okay, yeah, show me where I said 1 or 3. I'm not sure. This thing? The shifts?
Yeah, I suppose that as well.
Okay, this will produce the special number that I need.
Okay,
that's
1 in that operation.
Oh, it's start with the number 1. Okay. What a shift does is that you start with some number. It could be 1, it could be 41. And then you're shifting it in binary form by a certain number of bits. You're shifting it over. So what this did is that you started with the number 1. So we started with 1. And then we added in, we moved it to the left, 3 bits to bring in zeros.
Like 5, it would be the binary for 5.
That would be, if we said 5, left shift 3, what it would do is you'd start with 5, 1, 0, 1. And then you move that bit, those bits to the left by 3. So that brings in 3 zeros, which would produce 5 times 8. So 40, I guess. Yeah. So that's how you can immediately or easily get a number, get some bits into a position that you care about. And that's usually most useful with starting with 1. Like the 1 is in bit 0 right now, move it to the bit I care about. Yeah? Yeah, those are good questions. Does that make enough sense for now? Very good. Yeah, any other questions? Explain. Yell at me until we get it. That's the whole point of me standing up here right now. Get your money's worth. All right. There is a trick, though. Let me show you the trick. I want you to try this, too, though, at the end, if you can. You can do it in one line again, if you think about it. Starting with this number, what can I do each time, if I do the same thing each time, to get something with some number to go from there to there, and then also from here to here? Like, what could I do here? The trick is going to be in the new operator. It's going to be exclusive OR. Do you see how that's going to, like, if it was a 1, like, true and true becomes not true, but it makes it false? that's going to be the secret, right? But if it was like 1 exclusive OR with 1 becomes false, 0 exclusive OR with 1 becomes true. So that'll give you the flipping that you need, all right? That's the trick there. So if I did an exclusive OR with this number, with this special number, 0, 1, 0, 0, 0, 0, so the number with the 4th bit set, do you see how that would preserve everything because they're different? Or a 0. That would preserve all the other bits, and then it would flip this one because it was, all right, 0 exclusive OR with a 1, that makes a 1 because they're different. And then if you use that same number and you exclusive OR with the same number with the other one, 0, 1, 0, 0, 0, 0, that would do the same thing. It would preserve everybody else. There they are. And then, now they're the same though. It makes it a 0. See that? So that's the trick way of doing it. But you could do it the longer way, and that would make the most sense. All right. So conclusion now is exclusive OR with a number with the 4th bit set, which is 1 left shifted by 4. Okay, whatever that is. 32, I think. 1, 2, 4, 8. Oh, 16. Sorry, 16. So x caret 1 left shifted with 4. But we could have done it the other way. Could have done it with an if statement. Could have been like if x ANDed with 1 left shifted with 4 means was equal to 0, right? All that. That means it was unset, right? Set it. Else, that means it was set. Unset it. And you could do with an or, right? With an or this would be like with an and then the tilde. Okay, so that's the long way. That's the short way. Are there any questions about that? That's a good little example, I think. Those are your 2 options. Yeah, if you can formulate questions, please yell at me with them. I would like to help. Okay, so I guess this might all seem silly and like, why would I care right now? I'm never going to make a very memory-intensive video game ever. Just let me work in Python all day. Why should I care? All right, here's some reasons. Okay, eventually in an upper division class, you'll be forced to at least make some version of a compiler. You may work on a compiler one day. If you're making a compiler, you must make binary numbers. Because deep down, right, if you ever tried to use Vim on some compiled thing, it's a bunch of garbage, because what's really going on is it's just a bunch of 1s and 0s. So really it's like, this is what the program looks like. It's a bunch of like 1s and 0s, and you can encode that in hexadecimal more easily. That's the program, just something that the CPU can understand. And here, let me do this one. Dump-d bitwise. Where's the main function? So here's what the main function looks like in CPU instructions. I'll have to wait till CSCI 45 to fully understand this, but like here it's doing some stuff. Here's my main function. It's a bunch of little, they're called assembly instructions. And then like we're calling functions and like doing stuff and like moving values around to do what I need to do here. Like this move instruction that moves some important information around, it's represented exactly as this in binary. All right, that's what the CPU is seeing. It's seeing bunches of 1s and 0s. Like, oh, okay, that's a move. I need to do something. And do you see how here are 2 move instructions? They're moving different things around. Do you see how they start with the same bits? They end with something different. If you were making a compiler that emitted binaries, you would have to like, all right, let's OR with these bits to get them in the right position, the 4, 8, 8, 9 in hex. And then like, all right, if I'm moving these particular things, I need to put a D6 here. If I'm moving these particular things, I need to put a C7 here. So I'll OR with the right ones. If you're generating binary ever, you have to care about bitwise. It's like put in the pieces that are the same and then make them a little bit different. So that's one reason you should care, all right? Just the way that you make instructions inside of a computer. If you ever work in anything low level, you need to care about the little bit patterns for all your instructions. And then, probably something that you'll be more interested in doing is like every image file, every JPEG, every movie, right? It's all encoded in binary, is it not? It's just a bunch of 1s and 0s at the end of the day. And if you ever want to do something, you ever want to make a program that works on an image, kind of like we were doing before, but it's in binary at that point, just to get pieces out of that image file. Like, all right, where is the image size saved? Like, it's a byte offset this. You read these many bits, and like that's where the number of the size of your image is. The width and the height are in these bytes, something like that. If you wanted that information, or you wanted to change the pixels, you have to go into individual bytes and mess with them. So that will involve you messing with bits, all right? Going and shifting around and moving to where you need to go, okay? So those are some good reasons why you might want to care about this stuff, even though it kind of seems very pie in the sky right now, confusing as well. Like, one day you will need this, all right? So that is bitwise operators in a nutshell, and I think that's where I want to stop for the day. Are there any questions about any of this that I could answer? Okay, good for now. It's good to study the code for sure. I know it is a new, weirder topic. And let's see. Yeah, I think that's all that I wanted to do for the day. So yeah, the rest of the time is all yours.